Thank you. Welcome to our talk titled Kernel Mode Threats and Practical Defenses. So first, a little bit about us. I'm Joe Desimone. I'm a senior malware researcher at Endgame. I have an interest in offensive security research, but my day job is development of endpoint protections.
Hi, I'm Gabe Landau. I'm a principal software engineer at Endgame. I take apart malware, figure out how it works, and figure out ways to stop it.
So here's our agenda today. And our talk is going to focus on kernel mode threats as they apply to the Windows operating system. And it's split into 3 parts. So in part 1, we're going to explore sort of the last decade of the cat and mouse game between kernel mode malware authors and also the OS protections that are designed to mitigate them. Next, we'll move into part 2, where we're going to dive into our own offensive research, where we identify gaps in the OS protections and basically discover that they're not adequate. And finally, in part 3, we're going to explore ways to augment these OS defenses. And this is going to be both by leveraging existing publicly available tools along with innovative approaches to closing gaps. So quickly, why this talk? Why kernel mode research? Well, kernel mode threats, they're significant because they generally have total control over the affected machine. They can essentially rewrite the rules of the operating system and easily tamper with security software because they run at the same privilege level. APT groups have realized these benefits and are basically actively exploiting them to stay ahead of defenders. So we hope this talk increases the community's exposure and ultimately improve the industry's defensive posture against these threats. So basically, the first generation kernel malware, roughly about 10 years ago is really when there was true widespread kernel threats came onto the scene. At the time, there was basically no defenses baked into Windows to counter these threats, so they flourished. Rustock, TDSS, ZeroAccess were a few big ones where they had botnets that numbered in the millions. They all shared a similar technique for gaining ring 0 code execution, which was basically to infect drivers on disk, and when those drivers would load, they would get their kernel code execution. They also commonly deployed rootkit style technologies, so hiding files, network connections, registry keys, that sort of thing. So in response to this widespread malware, Microsoft released 2 protections. The first was PatchGuard to directly go after the rootkit techniques that they were using. So basically, PatchGuard will continually scan the system and look for hooks or modifications of kernel data structures, and if anything is detected, it'll crash the box. PatchGuard itself is not perfect. It can be bypassed, defeated in a number of ways, but it's continually evolving, so that makes it a moving target for adversaries. So what they write today might be caught by PatchGuard tomorrow. And the next protection is driver signature enforcement, so also known as DSE. And DSE requires that all drivers have to be signed by a valid signature before they're allowed to load on the system. And this was originally on Windows Vista. And basically, it blocks malware that's trying to infect drivers on disk because it's breaking the digital signature. It also prevents just unsigned malware drivers from being loaded. Both of these defenses were originally for 64-bit systems, and when they first came onto the scene, it wasn't 64-bit operating system market share was very low, and it became a lot more important as people started shifting over to 64-bit Windows versions. So in order to evade these both driver signature enforcement and in some cases PatchGuard, malware authors began moving to bootkits. So basically, bootkits tamper really early operating system boot code, such as by modifying the MBR or VBR or any other OS-specific bootloader code. And basically, get code execution before the OS even starts up. And there's a number of different bootkits over the years. One of them, Xpatch, was notable. It actually hooked the system so early on that when PatchGuard would first initialize itself, it would scan through the changes that it made and basically trust those changes. And then if you tried to unhook it or tamper with the rootkit, then it would crash the box. So it was effectively protected by PatchGuard. I thought that was interesting. So to counter bootkits, basically the solution was SecureBoot. And with this technology, the system firmware itself actually validates the digital signature of the bootloading code before transferring control. And recent advancements have actually moved this verification check even earlier, such as Intel BootGuard. There's been a lot of research recently in basically planting malware in the firmware itself. So it's basically you want the chain of trust to start as early as possible, where now you can even have that chain of trust go all the way back to the hardware itself, and the CPU will validate the firmware before transferring control. So driver signature enforcement, SecureBoot, and PatchGuard have definitely dramatically reduced the overall volume of the commodity kernel mode threats. We don't really see botnets numbering the millions of using kernel mode malware anymore. It really has not stopped the continuous backdrop of APT level threats that were using kernel mode techniques. And one of the really common themes among APT level kernel malware has been to actually install a legitimate, signed, but vulnerable driver on the box and then exploiting that in order to gain kernel code execution, thereby sidestepping driver signature enforcement. And another technique that's notable is just to steal a digital certificate from a legitimate company and then just sign your malware with that, which gets you loaded and also makes you look a lot more legitimate on the endpoint. Even more advanced nation-state threats, such as Dooku, don't even bother with bringing a vulnerable driver. They'll actually exploit the kernel directly with a 0-day. So Dooku 2.0, for example, exploited a vulnerability in win32k.sys. It was also notable that it did some kernel hooking of the Kaspersky driver. And basically what this did was allowed them to convince the Kaspersky driver that their user mode injected code was actually trusted Kaspersky code. And this is not really a vulnerability with Kaspersky. This is kind of a problem in the inherent trust that you have once you gain kernel code execution. But basically, Kaspersky would whitelist their process completely, wouldn't alert on anything, and it would also protect that process from being terminated by the admins or other security software. For actual persistence, the Dooku 2.0 actors also, they used a malicious sign driver from a stolen Foxconn certificate. And basically, they would drop that on certain computers on the network that had external access. They would connect into that computer and then route their malicious traffic to internal machines from there. DoublePulsar is also worth a strong mention, which is basically a lightweight kernel mode implant that lives only in memory, no reboot persistence. And it's typically loaded onto a system using a remote ring 0 exploit, such as Eternal Blue. And DoublePulsar allows attackers to basically get stealthy remote access onto the system and do network communications by hooking a function pointer in the SMB-v1 driver. And basically at the time, PatchGuard didn't care about this function pointer, wasn't checking it, so it was able to evade that. And when you actually connect into DoublePulsar, you can give it more kernel code to execute, but more typically you can pass it in a user mode module that'll then get injected that has a fully featured implant. It actually became pretty widespread after the code for DoublePulsar was leaked, so it's been picked up by other adversaries and used, for example, like in the WannaCry attacks. To mitigate these more advanced attacks that are exploiting their way into the kernel, Microsoft released virtualization-based security, or VBS. And basically with VBS, the kernel itself is no longer considered trusted. It's sandboxed by a hypervisor. And there's a number of technologies built on top of virtualization-based security. One's hypervisor code integrity. And hypervisor code integrity, known as HVCI, basically requires all kernel code to be signed, and it's enforced by the hypervisor. You can't have read, write, execute memory. HVCI basically stops a number of kernel mode threats, including DoublePulsar and also things like Turla driver loader. And then other technologies like CredGuard use the hypervisor to protect credentials from the system from tools like Mimikatz. So this chart kind of summarizes what we've kind of talked about over the last decade. We've got the attacker techniques and the corresponding defenses. So in the upper left, originally malware authors are going nuts. There were no defenses whatsoever, just loading their code directly into kernel mode. From there, Microsoft released PatchGuard and driver signature enforcement. Attackers then moved to using bootkits, which was then countered with SecureBoot. And then adversaries started using exploitation in order to load their code in the kernel. And then finally, Microsoft released virtualization-based security to counter that. And just to kind of show, we talked about some of the more important mitigations and protections built in, but there's actually a lot more that we didn't cover. And this just kind of shows that Microsoft has put a lot of investment into this over the years, increasing investment more recently. But one of the problems is the adoption rate. There's still tons of systems running Windows 7. So if the protections are only in the latest and greatest version of Windows 10, then a lot of people are not getting that benefit. Okay, we're moving on to part 2, where we're going to deep dive into our own offensive kernel mode tradecraft. So Endgame, the company we work for, periodically conducts internal red versus blue exercises, both to test our product and to test our own skills, basically from a red and blue perspective. Gabe and I are on the red team, and basically we're tasked with emulating adversaries from varying sophistication levels. So we want to try to emulate a really noisy, commodity actor, but we also want to try to emulate the most advanced APTs to sort of gauge like where our blue teams are at and how well they can detect it. So as far as the more advanced technique, typically what we had done in the past is to just live sort of fileless techniques in user mode, but our blue team was getting much better at detecting us with these techniques. They were basically upping their game. So in the last iteration of our red versus blue, we decided to up our game, and we looked at doing kernel mode techniques and to try to evade detection. And at this point, personally for me, I hadn't done kernel mode development in a while, so I had to start from scratch, my build environment, debugging environment, and I just wanted to share, if you're new into kernel development, definitely put time into getting your debugging setup down to the point where you can build a driver, get it loaded into a virtual machine, load it in the virtual machine, crash the box, blue screen the box, whatever, and triage that so you can figure out what went wrong and then iterate on that process. So basically you'll get really good really quickly at triaging blue screens. If you can get the total time for that process down to a couple minutes, then you can compensate for not really knowing what you're doing. Like, I don't really know what I'm doing. I can just read documentation and sort of try out things, crash, okay, no, go back, and keep repeating that process, sort of brute force my way through it. But one of the key components that we wanted to use in our kernel mode implant was going to be Turla driver loader. So this is written by Firefox on GitHub. It's freely available, and basically it's an open source implementation of the Turla exploit that they use to get code execution. And in a nutshell, it'll basically drop a VirtualBox driver, install it on the system. It'll exploit this VirtualBox driver to execute shellcode in kernel mode, and then the shellcode will basically memory module style map a driver into kernel mode without it touching disk. So that basically helps us achieve two objectives. We want to live in memory as much as possible and also evade the driver signature enforcement checks. Also, for our implant design, we had some high level goals. So we wanted it to be kernel mode only. A lot of the kernel malware that we've talked about typically use a hybrid where there's some kernel components and there's also some user mode components. Typically the kernel mode component will be as lightweight as possible, and they'll inject the full payload into user mode. But since our blue team was really good at catching anything injected in user mode, that worried us, so we didn't want any user mode component. We wanted the implant to be fully kernel mode. And that meant we had to figure out how to actually talk to our driver over the network. Thankfully, Microsoft has a library for actually doing this from kernel mode, and it's called WinSocket Kernel. And basically, it's really well documented. There's a lot of sample source code that you can use. So we pretty much just, read through some of the documentation and copy pasted huge chunks of their sample code in order to get kernel mode network sockets up and running really quickly. We also wanted it to be triggerable inbound. Our red versus blue environment doesn't have a whole lot of legitimate activity going on, so we thought we would stick out if we were like beaconing out. We would rather have the implant lie waiting, stealthy. We can connect in at any time of our choosing and go interactive. And then finally, we didn't really care much for features of the implant. Really basic stuff like file upload and download was going to be perfect for our use case. Now, leveraging Turla driver loader was going to be a problem if we just downloaded it and ran it as is, because Turla driver loader is just an executable that would run off disk. So that was going to be a big problem for us. Our blue team has access to AI malware detection, so we were really worried about dropping any sort of executable to disk. So we really wanted to get that loaded through reusing fileless techniques that were available. You could do this through a number of different scripting libraries. Like you could map it right in PowerShell. That one, depending on what security software is running, could have visibility into PowerShell. At the time, Squibbly-Doo by Casey Smith was sort of like the new hotness. And basically that was leveraging Reg Server 32, and you could download what's called a scriptlet that contains JavaScript code over the network, and you could execute your JavaScript code in memory. From there, you can use a tool called .NET to JS, written by a Google Project Zero researcher, James Forshaw, and you can basically map a full .NET module into memory from JavaScript. And then once we have .NET code execution, we can pretty much do whatever. We have full access to Win32 API. We could have exploited the driver from here, but we already had the TDL code in native C code. So instead, we just used basically memory module techniques for mapping that into memory. So we had a .NET memory module, which would then map TDL into memory, and then we transfer execution to TDL, which would then exploit the driver and then install our implant into kernel mode memory. Another thing we examined was actually keeping the legitimate driver off of disk, because technically that was the only thing that was being written. We looked at using WebDAV for doing this, which is one option. There was kind of an interesting sysmon bug where it didn't really like the path very much for that. It couldn't recover the hashes, which I thought was interesting. So we talked about WinSocket kernel, and in the sample code that we had, it would open a port on the system. This definitely was not stealthy by opening a port. You know, you'd have to worry about firewalls and stuff. We wanted to do something better. So we kind of reused the idea that DoublePulsar had of corrupting a function pointer in order to hook stuff without triggering PatchGuard. But we didn't want to pick the same function. We figured now maybe PatchGuard is, you know, caught onto that and might be scanning that. So we started looking through various other drivers to figure out a good function point, or a good hook point. And we settled on the server net driver. And basically, this shows the process. The server net driver is responsible for opening port 445. And these are the functions that it goes through in order to actually open up that socket. And on the far right, you can see the server net WSK accept function. Well, we actually have an egg hunter that'll search for that pointer in memory. And we basically hook that with our own accept function. And when you connect in the box on port 445, we get redirected to our code. We can basically decide at that point, hey, do we want to hook this connection and use that for implant comms, or do we just want to pass it back to the system silently so that people can still use SMB file sharing and stuff like that? So I'm going to show a demo of this tool.
It looks good.
Okay, so basically, when we did this back at our last red versus blue, the current hot trend was using squibbly do, but we kind of want to refresh this for this talk. So a very recent technique by Matt Graber and by extension Casey Smith is known as squibbly 2. And basically, the idea is you can execute XSL files which contain embedded JavaScript code. And Matt Graber actually took this a step further by figuring out how to inject it into a legitimate signed VBS script. So on the screen you can see you can execute C script with this winrm.vbs. This is a valid signed driver. And then in the same folder you can basically plant this file wsmpty.xsl, which will then start executing your JavaScript that's embedded in there. So, you know, this is kind of a new technique. It's released in the last few weeks. So we wanted to leverage this. So basically we execute that. It goes through the various stages very quickly in order to map the code into memory and exploit the driver. And then from there, we have a Python controller that we can connect in. You know, we can get some basic system information. We can download files from there. And just to show the kernel socket hooking technique, you can see we're connected in on port 445. Over on the right, you can see the PID there. PID 4 is associated with the system process, basically associated with the kernel. Okay, so that was really cool. You know, we did really well on our red versus blue. Unfortunately, that meant we had a lot of work to do to sort of improve our tradecraft, because, you know, our day job is actually defense of these systems. So we're like, okay, yeah, now we got to work on that. But when we actually got accepted to this talk, we actually wanted to push it even further. So I talked about virtualization-based security a little bit. And virtualization-based security combined with hypervisor code integrity, like I said earlier, will block any unsigned code from executing. That includes both, you know, DoublePulsar, TDL, and by extension our implant that we use in our red versus blue. So, okay, what can we do to actually evade HVCI, the latest Microsoft mitigations, and get code execution? Well, we started with trying to load our VirtualBox driver, and that was a no-go. It's completely blocked from loading. I think that it's just generally incompatible with HVCI, so it's not allowed to load. And our first step was going to be we're going to have to find a new driver to exploit. So at greyhathacker.net, there are a ton of POCs that this guy, Parvez Anwar, has done some fuzzing or analysis and found vulnerabilities in various drivers of software you've never heard of. But that was kind of a good stop for us to shop for various exploits that we could reuse. We started off with one vulnerability that it was like a static 1 byte write to anywhere in kernel mode memory. Well, the problem with that is you'd have to corrupt some kernel heap memory in order to actually get a full read-write primitive. It would have been a lot of work. If you can choose the vulnerability that you're bringing, I would just say choose wisely. Make it easy for yourself. It also makes it a lot more stable. So we found another vulnerability that basically gave us a full read-write primitive right from the driver. So we could read and write 8 bytes of memory wherever we want in kernel mode. So that on its own can be used for data-driven attacks. So HVCI prevents unsigned code, but it does nothing to protect against general kernel tampering. So basically, you can still corrupt key data structures in the kernel and in any drivers that are loaded. For example, you can modify the import address table of certain drivers on the system, just like Dooku 2.0 did on the Kaspersky driver. You can, knock them out, make them do nothing. You can disable EDR, kernel to user communications. You can disable security focused kernel ETW providers, such as Microsoft Windows Threat Intelligence. You could also elevate privileges by modifying tokens or handles from kernel mode, and basically a variety of other data corruption attacks. So one example of this, we actually looked at Sysmon, and we were curious, what we could tamper with Sysmon just from a data perspective. And this is nothing against Sysmon. It's just, freely available. We can download and play with it. It's definitely not a Sysmon specific vulnerability. But what we did was basically found the chunk of code that's responsible for sending events from kernel mode to user mode. So you can see there's this IOCSQ remove next ERP function up here. And if you replace the pointer in the IAT to basically a return 0 ROP gadget, then all this code here is going to get skipped over. And this code right here is actually what's responsible for sending the events down to user mode. So if you skip this, then no more events from Sysmon. So, if you want to be a little more sneaky, you could probably selectively drop certain events. There's a structure that gets passed into this function that actually contains the PID associated with it. So you could selectively drop things for your implant. But in this example, I think it was good enough for our purposes. And this is sort of that example of tampering with the ETW providers in the kernel. So there's this registration handle that's referenced in all the functions that are responsible for process injection. This is the way that, Microsoft products can monitor for various process injection events. Well, if you modify this handle, then, these functions will basically just fail silently. Okay, so we can do data corruption attacks. That's cool. But we really wanted to get kernel code execution. And we were clued in by a talk by David Weston, who's the Windows Offensive Security Team Lead and Windows Device Security Manager. He did a talk at Blue Hat IO. And their own red team was working to try to defeat HVCI. That's what they do. And basically, they found that they could use code reuse attacks in order to execute what they wanted in kernel mode. And they actually worked on a mitigation where they would try to detect and block code reuse attacks, basically ROP, from working. But at the last minute, they found some unknown vulnerability in their implementation and found it wouldn't basically give them the level of security they wanted. So instead of shipping, half-baked feature, they cut it out, which is good for them. But that means there's still this hole available now that people can go after. Intel is actually planning on hopefully someday releasing hardware technology to detect ROP in kernel mode. There's specifications out there about it, but there's no chips available today that you can buy that actually have this in there. So basically, today you can do ROP with everything enabled, and you're free to do that. But for actually weaponizing this, we got an idea it was a Keen Team presentation from Recon in 2015. They talk about doing kernel stack hooking. So we have this read-write primitive, and we thought, we can do kernel stack hooking in order to get code execution while we're running under HVCI. And basically the way this works is you create a surrogate thread and put it to sleep by basically waiting for a mutex. And then you can locate its E-thread structure. Basically, from there's a pointer to the kernel stack associated with that. You can scan through the stack and find a function pointer like nt-wait for signal object. And you basically can overwrite that function pointer with a pivot gadget and use that after you resume the thread, that'll start executing, and then you diverted the flow of execution. So basically what this looks like is when you want to call a function, we dynamically build a ROP chain that's based on the number of arguments that are for the target function you want to call. So we had 10 gadgets were required for us to get basically a full N call arguments, or end argument function call, pardon me. And basically what that meant is if you're going to call a function with one argument, we'll generate one ROP chain. If you're calling another function with 8 arguments, it'll be a little bit different because you got to set up different parameters and stuff on the chain. And that's all done on the fly. So basically, you know, it starts off with that pop RSP return gadget, and that gets us to our actual ROP chain. The first step is we had a few gadgets that we needed to actually restore the data we corrupted on the legitimate stack. So we had to, you know, put back the original pointer that we overwrote. Then you have to set up the actual arguments for the function call you want. So you got to push things onto the stack. You got to set up things in registers. And then you actually call the target function to do whatever you want. Next, you can save the return value. You actually save that directly back to user mode. And then there was just one register that we basically couldn't dirty through this process, R14, which contained the mutex object. So we just had to make sure we replaced that and then unpivot the stack to complete the attack. So basically the end effect of this is you actually write your kernel mode implant in user mode, and each function call that you do is basically an exploitation of the driver, so our read-write primitive. So basically this is user mode code for doing like write process memory without, you know, doing open process or actually calling any syscalls. So, you know, this call function, you pass in the string of the function you want. So ps get current process, copy virtual memory, or the ones needed for this specific implementation. So with this, you know, you could inject into protected processes, you can evade detection by EDR and AV, etc. Show a demo of this now. Okay, so this is also going to go pretty quick, but basically we're going to run this POC.exe. What it's going to do is it's going to spawn a new instance of the Defender process that has a PPL or a protected process compatible signature. So you can actually create a new instance of that that's going to be protected. Normally you would not be able to access that process unless you had the equivalent level of protection on your process. So we're going to launch that, and then what we're going to do is we're going to use these ROP techniques all while HVCI is running. So you can see on the bottom, hypervisor code integrity is enabled, and basically use ROP in order to call a number of functions for giving us access into this process. So, you know, we're basically opening a handle to the process with from kernel mode and then duplicating that into our POC.exe, which gives us full access. Then from there, we actually just overwrote the entry point with some shellcode to pop cmd.exe. And you can see here, this is the Defender process with CMD as a child in Process Hacker. And if we open this up, you can see that the protection is full. So you normally not have access to this without kernel level, or some other techniques. But it's a good demo to show sort of what you can do by bypassing HVCI. Okay.
Thank you. All right, so up to this point, we've talked about how kernel mode threats and platform protections have evolved around each other. Then we talked about some offensive tradecraft that works even with the latest and greatest platform protections. In this final section, we're going to talk about how defenders can augment Windows built-in defenses in order to better guard their enterprises. And then finally, we're going to cover some aspirational research that we performed to further raise the bar. So first and foremost, the simplest thing you can do is event and hunt on driver loads throughout your organizations. There's readily available tools to do this, including sysmon, sysinternals, sysmon, and Windows Defender application control when you put it into audit mode. You should be looking for low prevalence and known exploitable drivers. It is important to build a baseline if possible. As many of you know, you have to understand your company's assets and infrastructure before you can begin looking for adversaries. The same applies for understanding the exposure of kernel modules throughout your organization. Defenders should employ hypervisor code integrity policies to block most legacy drivers. Ideally, you should be whitelisting driver publishers, but whitelists can be very hard to maintain effectively. At a minimum, you should see if you can mandate WHQL signatures, which stands for Windows Hardware Quality Labs. To get a WHQL signature, you have to upload your driver to Microsoft, which theoretically mitigates the threat of stolen private keys and certificates because attackers can no longer stealthily sign their malware. It also eliminates a whole swath of legacy drivers that were developed in the past. However, WHQL is not a panacea. So what you're seeing right here on your screen is the WHQL signature for the driver that we just exploited in the ROP demo. So to further their defenses, defenders can supplement code integrity policies with blacklisting of known exploitable drivers. Starting with Windows 10 Redstone 5, which comes out in October, hopefully, Microsoft will block many known exploitable drivers by default if hypervisor code integrity is enabled. It's great for some users, but not everybody has the hardware requirement that's required for HVCI. And a lot of enterprises are still on Windows 7 and Windows 8. So to help mitigate these risks, the risks of these forever days for the rest of us, we're releasing a tool called Kernel Attack Surface Reduction, or KASR, alongside this talk, that will block a list of known exploitable drivers. These are drivers that you can find on GitHub, where you run a tool and you pop the kernel within as quickly as you saw that demo. So we understand that this is only going to add a roadblock for unsophisticated attackers that are reusing known exploits. It doesn't scale, blacklisting doesn't scale. And it will not stop attackers who know how to find new exploits, new vulnerabilities, and then write exploits for them. But we're hoping it will at least stop script kiddies from rampaging around in your kernels. Microsoft is in the process of finalizing their Redstone 5 driver blacklist. When it's complete, we're hoping to incorporate it into a future version of KASR. KASR will be available on our website, endgame.com, sometime today. So looking back at our red versus blue, we realized that we needed a better way to hunt in the kernel for threats like DoublePulsar and our fileless implant. Traditional forensic style techniques of full memory capture and then offline analysis, they don't really scale to large or medium or large enterprises. So to address the problem, we decided to leverage the same style of collection techniques, but instead we would do the analysis on the endpoint. So this is similar to what traditional black box rootkit scanners have done in the past. This means we can complete a scan in milliseconds instead of minutes. However, there are several techniques available to read physical memory on a Windows machine, such as the physical memory device, or in the kernel, various MDL-based APIs. But our favorite technique is page table remapping. So processors use page tables to map virtual addresses into physical addresses. Page table remapping uses the CPU's paging system itself to read arbitrary physical pages. It requires very little cooperation from the OS memory manager, making it resistant to rootkits that, say, hook the virtual memory device, the physical memory device. The general idea of it is that you allocate a page of memory, and then you search and you find the page table that describes that page of memory. And there's a corresponding physical page for every virtual page of memory. Well, once you know where that page table is, if you're in the kernel, you can just rewrite that page table entry. So you rewrite the page table entry to point to a new physical page. And then afterwards you flush a CPU cache called the translation look-aside buffer, which is just caches the old value of that PTE. So once you flush that, you can now reread that same virtual address, which will be backed by whatever physical address of your choosing. Now, this technique is extremely fast, doesn't require any OS APIs, and it was our approach of choice. So our goal was to generically detect DoublePulsar as it lay dormant, without signatures. One option would have been to scan through the kernel pool, which is it's a heap in the kernel, the pool memory, looking for shellcode-like blobs. Unfortunately, on Windows 7, the entire non-page pool is executable, which leaves a large search space, and we're worried about false positives. So instead, we decided to identify the function pointer hook. But let's take a step back and say, what is a function pointer? A function pointer in a PE file, because all drivers are PE files, is just an absolute address. When a driver is built and is compiled and linked, it is linked with a preferred load address, and all pointers are addresses within that driver. So with modern operating systems, there's address space layout randomization, which means that drivers will never get loaded at the preferred load address. So to compensate for this, the PE file has something called a relocation directory, which is a list of all the locations within that PE file that need to be adjusted if a PE gets loaded here instead of its preferred load address here. So this relocation directory is basically a list of all the pointers within the driver file. So now, just by walking the relocation directory, we know all the pointers in the file, but we're interested in function pointers. Well, so if we narrow that list down to pointers to executable regions within that PE file, then now we have a list of function pointers. So we then qualify that even further, and we say that, okay, if it was a function pointer on disk, but in memory, it doesn't even point to anywhere in that driver file, but instead points to somewhere else that is also executable, then we consider that a hit. So this technique that I just described detects both DoublePulsar and the socket handler hook installed by our kernel mode implant. We're releasing a tool that, in our testing, can scan all drivers on a Windows 10 system in under, it's like 80 milliseconds, something like that. It's really fast. We're calling it MARTA, named after Marta Burgay, the first astronomer to discover a DoublePulsar. We'll demo MARTA alongside another tool in just a minute. So on-demand scans are great, but we wanted to see if we could take this a step further. So we wanted to see if we could catch in real time and potentially stop these types of attacks before they can do damage. So having worked on Endgame's hardware-assisted control flow integrity product, we're familiar with the performance monitoring unit, which is present on most CPUs, and the PMU is a component of the CPU that can be programmed to count occurrences of certain low-level events. And you can also program it to generate an interrupt when a certain number of those events has occurred. So in this case, after some experimentation, we settled upon indirect near-call branch mispredictions. When one of these events occurs, we program the PMU to generate an interrupt. Now, when the interrupt happens, our interrupt service routine executes, and we have a chance to validate and enforce a policy. So to detect unbacked code execution in this case, we keep a list of memory ranges that correspond to all the loaded drivers on the system. And when the interrupt occurs, we validate that the instruction pointer that was executing when the interrupt fired belongs to one of those valid memory ranges. And if it doesn't, we consider that to be a policy violation. So now I'm going to demo a real-time detection of DoublePulsar, and it's also going to show MARTA. All right. So first thing I'm going to do is I'm going to start the unbacked detection driver. Next, I'm going to do a MARTA scan, and MARTA's not going to find anything because we haven't exploited the kernel yet. Next, from a second VM, I'm going to launch the Eternal Blue exploit. And in just a second, when the exploit succeeds, you're going to see a break into WinDebug. That's our detection driver. And it's going to print out the instruction pointer that it detected as unbacked. There it is. All right. So first, we're going to check out that address, and we're going to see it doesn't belong to any driver module. In fact, it belongs to the HAL reserved range. We're going to look at the call stack here, and we're going to see that servnet is calling some unbacked code. Right here, servnet.sys. Now, if we look at the actual instructions of that are executing, we're going to see here that it is this architecture determination shellcode. This shellcode will work on both x86 and x64. It uses some tricks to figure out which architecture it's running on. Finally, we're going to rerun MARTA. Because we allowed the shellcode to execute, it successfully installed a hook into serve.sys. And MARTA detected it. And by the way, MARTA is actually faster now. This was an older version.
Debug build, probably.
Yeah. No, we added some optimizations also. Yeah. So that is detection of real time. All right, here we go. As well as demo of MARTA. All right. So there's weaknesses to this proof of concept, including the fact that PatchGuard itself uses unbacked code. So, because they're trying to hinder reverse engineering. So while it's fun to catch PatchGuard, this false positive would need to be addressed in a reliable and robust manner, which is difficult given the fact that PatchGuard is undocumented and subject to change at any time. Another weakness is that kernel code, so if the adversary can execute kernel code and they're aware of the system, the first thing they could do is disable the PMU. All you need to do is write some MSRs to disable the PMU. Or they could disable interrupts entirely. And finally, an attacker could always do data attacks on our driver, just like before, where you could do IAT patching, things like that. Because this is a driver. This is just software running in ring 0. All right, so I just want to cover quickly, there's some notable work in this space. We're running short on time. Hypervisors that do similar things, but instead of using PMU, they use hypervisors, including MemoryMon, AllMemPro, and SecVisor. Additional details are available in our slides, which will be posted online at the end of the day. So earlier we mentioned that the Windows kernel has a gap in coverage against rear flow control hijacks, ROP attacks. So Microsoft canceled Return Flow Guard, and their current plan to defend against ROP requires Intel Control Flow Enhancement Technology, or CET, which to our knowledge doesn't exist on any production processor today. When it is released, it will only benefit processors that are, the systems that are running those processors, which is great for the future, but it doesn't help anybody today. So here we propose a PMU-based protection system. So we can configure the CPU's last branch recorded mechanism to keep a circular log of all of the return instructions that occur within the kernel. We can then generate a control flow policy by scanning all the drivers that are loaded into the kernel, performing a linear scan disassembly of those drivers, looking for call instructions. Every call instruction, under normal control flow, the next instruction after that call instruction is the expected return site. You call somewhere else, it returns back to the next instruction. So we build up a policy for every driver on the system that's a bit map that just says where the bit is 1 if that's a legitimate return site, and the bit is 0 if it's not a legitimate return site. And we do this for every driver on the system as we start up. This is what we're calling a policy. As new drivers are loaded into the kernel, we update the policy accordingly. So generating an interrupt for every return instruction is too costly. So instead, we exploit the fact that ROP, or return-oriented programming, tends to generate a lot of branch mispredictions. And this is because CPUs, the branch predictors in CPUs were not optimized or designed to work well in ROP scenarios. So there tend to be a lot of branch mispredictions in these scenarios. So we can program the PMU to only generate interrupts when there are branch mispredictions in the kernel. And then finally, when one of these interrupts fires, we look at that whole circular buffer of the LBR, the last branch recorded system, and we validate that each of those is a valid return site. And if one of them is not, we consider that to be a policy violation. So one thing I'd like to say, if you don't tune these systems properly, they can generate way too many interrupts, and they could adversely affect system performance. With the system tuned, as you're going to see it in our upcoming demo, we saw about a 1% reduction in the Jetstream browser benchmark, while still maintaining 100% detection against our sample exploit. We were using this as a rough approximation of user experience. All right. So here I'm going to demo ROP exploit. This is Windows 10, 1803. Hypervisor code integrity is enabled. First thing I'm going to do is I'm going to start up our detection driver, and it's going to parse every driver that's loaded into the kernel, generate those policies, and build and store them in fast lookup data structures. Next, I'm going to launch an exploit against that WHQL driver that's loaded into the kernel right now. And right here you can see there's the 4 ROP gadgets that this exploit's going to use. We run the exploit, and our detection driver prints out the return destinations, and we can see that we catch all 4 ROP gadgets. So, getting into weaknesses and limitations. So like any other driver, this driver is vulnerable to data attacks, like IAT patching, etc., or attacks on our policy bitmaps. And just like before, the PMU can be disabled by an adversary with ring ZeroAccess. However, both of these issues could be addressed with a hypervisor. The hypervisor could create and maintain the policy bitmaps, just like they do with Control Flow Guard, and they keep those bitmaps read-only to the kernel so they can't be tampered with. The hypervisor could also prevent tampering of the MSRs that control the performance monitoring unit as well as the last branch recorded mechanism to keep them from being tampered with. Another issue is that in order to performantly and accurately determine control flow, we need both the PMU and the LBR. This means that if this system is running inside of a hypervisor, the hypervisor needs to make both of those CPU functions available to us. This is not currently true on Hyper-V or VMware. VMware does expose the PMU, but not the LBR. However, the VBS or virtualization-based security hypervisor in the newer Windows 10, newer Windows 10 security feature does make it available. So it is available on native hardware if you have HVCI enabled. This system does depend on being able to accurately determine valid return sites, which means we need to build remember I was talking before about the call and it needs to have the return site immediately afterwards. Well, unfortunately, there's two drivers that are loaded into the Windows kernel by default that are obfuscated. clipsp.sys and peauth.sys. Because they're obfuscated, they do weird things like push ret that make it difficult to determine all the legitimate return sites. So we have to currently ignore all returns into those drivers, which creates a huge gap. This could be addressed by Microsoft if they were to have their obfuscating compiler emit a list of valid return sites while it's doing its obfuscation, and then those return sites could be used for policy generation. So finally, I want to give credit to George Wachurski. In a testament to there's nothing new under the sun, we very recently found out that he invented a similar system a couple years back implemented against Linux. So today we talked about how Windows kernel security has evolved over time in response to threats. We then discussed some discoveries that we as red teamers made, and then we put our blue shirts back on and discussed some ways to close these gaps. Windows platform security has gotten a lot better in the last decade, but there's still big holes that will need to be addressed at some point. There's steps you can take though. You should be upgrading to Windows 10. You should be enabling your TPMs, SecureBoot, hypervisor code integrity. Implement a code integrity policy that requires extended validation and WHQL signatures. If possible, go even stricter and implement a whitelist of allowed publishers for your organization. Use a signed code integrity policy, because if you don't sign it, it can be just replaced by the attackers. They might have to reboot the system, but whatever. And then finally, monitor and hunt on driver loads throughout your organization. Have any questions?